Hello everyone, welcome to EDCON 2020 Lockdown Edition, and this is my presentation on weak subjectivity in Ethereum 2.0. I'm Aditya Asgaonkar, and I'm a researcher at the Ethereum Foundation working on Ethereum 2.0 research and development. I'm going to start out with what weak subjectivity is, and then move towards the specifics of what this means for Ethereum 2. And I'm going to end with a call to the community of some actionable items and what this means for end users who are the stakers of Ethereum 2. So let's start out with some definitions. An objective protocol is one where any two nodes on the same network who are seeing the same set of blocks can uniquely identify the same main chain. And a subjective protocol is one where nodes on the same network who are looking at the same information, the same set of blocks, can arrive at different conclusions about what the main chain is, or probably even remain inconclusive of what the main chain is. Let's look at what this means in terms of two popular consensus mechanisms for blockchains, that is proof of work and proof of stake. So for proof of work, the consensus mechanism is simple. It's just the longest chain rule. And since block production is rate limited by extrinsic factors such as the speed of the fastest hardware available, we have some probabilistic guarantees that there cannot be two longest chains at the same time, which means that there cannot be two main chains at the same time. In proof of stake, the consensus mechanism is the finalized chain rule, and finalized here meaning that some BFT consensus mechanism has come to consensus on that block. So finalizing blocks is a completely intrinsic process, meaning that just the correct signatures from the validators on that blockchain are required. So it is definitely possible to have two finalized chains, but the guarantee that we have from our consensus mechanism is going to be that a lot of stake has to be burnt in order for this to happen. So usually it's going to be a 1/3 threshold, which means if there are two finalized forks, then at least 1/3 of the stake has to be burned to allow this. So what does this mean in terms of the block structure? So proof of work, we are a node on a proof of work blockchain, and we end up seeing these set of blocks. So we start syncing from the genesis, and somewhere down the line we encounter a fork, and one of the forks ends at height 100 and the other fork goes up till height 150. So just by looking at this, we can reject this fork completely and safely say that this is the main chain, because our consensus mechanism is that the longest chain is the main chain. In proof of stake, if we encounter this kind of a block structure, and we start syncing to it, where we start with the genesis, we come down to height 129, and we encounter a fork. So both of these forks start at height 130. One of them ends at height 145, and there is a finalized block at the end of it. And the other one ends at height 150, and there is a finalized block at the end of it. So we are definitely not able to determine which is the main chain, because our consensus mechanism said the main chain is the one which has been finalized. And over here, both these conflicting forks have finalized blocks at the end of it. So we have experienced a consensus failure, and we cannot determine uniquely what the main chain is. So two nodes who are seeing the same set of information can arrive at different conclusions about what the main chain is. So what is weak subjectivity? The definition is as follows. Any two nodes on the same network and looking at the same set of blocks and having a recent state from less than n blocks ago can identify the same chain as main chain. So what does this mean? Let's look at the previous example. Let's set the n here to be 10 blocks. So for now, let's assume that this chain, this fork which ends at height 150 is indeed the main chain, which the rest of the network is considering its main chain. And since our n was 10, the weak subjectivity state, which is going to be kind of a checkpoint state from n equals 10 blocks ago, is going to be from over here at height 140, and we are trying to sync to the network, and the information available to us is these set of blocks and the weak subjectivity state from height 140. So we start syncing, we encounter these forks, and we encounter the block at height 140 in both these forks, which is somewhere here, and we can kind of reject this fork because the state is not going to match our weak subjectivity state. Whereas in this fork, we encounter block 140, we find the post state of that block, and it matches our weak subjectivity state, which gives us a guarantee that this is the main chain. So any two nodes who have this exact set of information is going to arrive at the same unique conclusion. So now let's look at a popular attack on proof of stake, which is called long range attack. So in any proof of stake blockchain, validators on that blockchain have to be allowed to cash out completely from the system. Obviously, this is necessary because otherwise no one would want to stake. No one would want to accumulate rewards if they can never cash out. So the validators have to be allowed to withdraw their stake and completely exit the system. Now, the problem that this causes is after the validator has exited and their stake has been withdrawn, the keys of this previously active validator are now worthless. The keys are not securing the network in terms of like their voting power. They aren't securing any kind of stake. So the validator itself considers these keys as worthless. And now an attacker can buy these keys, which were previously useful, but now the validator has no use for them. The attacker can buy these for dirt cheap and try to cause havoc in the system. So what does this mean concretely? Let's say we end up in this situation to begin with, which is we started with the Genesis block. Sometime later, there is a block C0 where the validator set at that time was V1, V2, and so on till V100. And sometime after C0, there is a finalized block, C1, and the validator set there is X1 to X20 and V21 to V100. So there has been some change in the validator set here. Some validators from here have exited, V1 to V20 here have exited, and some new validators have entered, which is X1 to X20. So what the attacker has done here is forked off from block C0 and created a finalized block in a fork which is not the main chain, and the validator set at C2 is going to be V1 to V100, which means none of the validators from C0 have exited and no one new has entered. So this causes some immediate issues in our proof of stake blockchain. The guarantee that we must have from our consensus mechanism is that if there are two conflicting finalized forks, then at least 1/3 of the stake has to be burnt, at least 1/3 validators must be slashed. But since the validator set at these two finalized conflicting blocks is not the same, these guarantees are not going to hold. And specifically, since there is a 20% difference in these validator sets, the safety threshold that we have, which is the number of validators who must be slashed in case of conflicting finalized blocks, that number, which is usually 1/3, is going to drop by 20%. So instead of 33, only 13% of the validators will be slashed in this scenario. So how can this attack be concretely applied to a network? Well, let's say that we have a node which is trying to sync to the existing Ethereum network. Then the node is going to ask the network to send them the blocks. And these red nodes here are attacker nodes, which send the attacker's fork. And these two blue nodes are honest nodes, which send the honest main chain. So these attacker nodes are going to send C2 from the previous example, and the other honest nodes are going to send the honest main chain, which is C1. Now, from the perspective of the syncing node, both these forks have been finalized, and there is a consensus failure, and there is no way that the node can determine which the actual main chain is. So we definitely have a big problem on our hands here, and this must be rectified. And the way we do it is by using the concept of weak subjectivity, where the syncing node not only asks for blocks, but it also asks for a recent state from less than n blocks ago. And our duty here is to calculate what this n, what a reasonable value for this n should be. So why this attack only affects a subset of the nodes. So nodes which are already online at the time of the attack, from their perspective, it seems to them that a finalized fork has like suddenly appeared, and they can safely ignore this fork because well, they have been online and validating the main chain, and there was no indication of a fork before. In proof of work terms, this would be similar to a reorg. But nodes which try to later sync to the network will definitely not be able to not have access to the extra information that the nodes which are online have, and they won't be able to determine which the honest chain is. So the question we must ask to calculate the n for our weak subjectivity state is that what is the most recent such C0 from where the attacker must fork, so that the attacker experiences a slashing of lesser than 1/3 minus d fraction of validators. This 1/3 minus d is going to be the new safety margin of our proof of stake blockchain. So instead of it being fixed to 33%, that is 1/3, it's going to drop down by a factor of d, and we'll call this the safety decay. And let's calculate what this most recent C0 should be for various values of d. So after some calculations, we arrive at this table, and for more in-depth analysis, you can follow this link. So over here we see that so this is kind of the duration of the most recent C0, which is the weak subjectivity state or the weak subjectivity checkpoint, and it depends on what the value of safety decay d is set to be, and it also depends on the size of the validator set. So it depends on the validator set size, because that number determines how fast validators can exit and enter the system. So obviously that determines how fast an attack of such kind can be conducted. So the number we are aiming for here is going to be 10% safety decay, which means our consensus guarantees that at least 33% minus 10% of validators are slashed for conflicting finalized checkpoints, and for more than 260,000 validators. This duration of the most recent C0, which is the weak subjectivity state, is going to be 3200 epochs, which comes out to be somewhere around 2 weeks. So this means that nodes which are syncing to the network need to have access to a recent state from within 14 days ago. And so we come to a call to the community, which is that providing this latest weak subjectivity state from within 14 days ago is essential to the security of the network. It allows syncing nodes to uniquely determine what the main chain is, and leaves them and renders them invulnerable to such kind of long-range attacks. And we expect that organizations or users who are running Ethereum 2 nodes can provide the state on their website or through some other channels. And if not the entire state, then at least some kind of a checksum or a commitment to the state can be provided, so that syncing nodes can obtain the state from elsewhere, but still verify from users that they consider honest what basically the authenticity of this weak subjectivity state. And which organizations or users might these be who are sharing this weak subjectivity state? Well, the most natural kind of choice for this, or the most natural actor who kind of has this duty is block explorers. So Etherscan, Beacon Chain, Block Explorer, etc. can provide this service. Large companies who are invested in the Ethereum ecosystem, maybe something like Consensus, etc., can provide this service. Client development teams. So within the Ethereum 2 research and development group, we've had a lot of discussion on whether client development teams should host their own nodes and provide these weak subjectivity states to users of their clients. And the general feeling seems to be that it should not be a duty of the client development teams to kind of do this. It's a big fiduciary duty, and there's ongoing conversation about this. The last major actor who might be responsible for this can be Ethereum Foundation, but that requires a larger discussion and debate in the community. And there are a lot of open questions that this has, which is who must be providing these weak subjectivity states and what is the justification for them doing this. And is there a need for a technical standard for the distribution of these states? Maybe something like, should it be verified using checksums? Is there a signature standard needed, etc.? And for users who are curious as to what this means, providing the state is actually not that expensive. The total state size depends on the number of validators in the system at that point. So for 100,000 validators, the state comes out to be around 18 megabytes. And for 1 million validators, it comes out to be somewhere around 130 megabytes. So it's not insanely huge. The state is kind of relatively small, definitely a lot smaller than the ETH1 state. And for curious people who want to calculate the size of the state, the fixed amount is kind of 6 megabytes total. And for every 10,000 validators, you can add 1.2 megabytes for it. So what might this look like? What might this look like for users who are just starting up their nodes and trying to sync to the network? Well, this means that well, first they have to download some client software, and before syncing their client software to the Ethereum network, they have to download a weak subjectivity state from some provider. And for example, this could be like my own personal website where I'm providing this weak subjectivity state. So maybe, for example, this in the Medasha testnet, if the latest weak subjectivity epoch is 1234 and the checksum is this, the user can download the state, verify the checksum against this, and maybe the user can navigate to some other weak subjectivity state providers and see what the checksum is from them and what the latest epoch for the subjectivity state is, and kind of verifying their own network of trust, and download that. After downloading it and verifying its authenticity, the user must input that into their client, maybe as a command line parameter or something else. A standard for that is yet to be set. With this information, the client software should be able to reliably sync to the head of the main chain. So something like this is kind of essential to the security of Ethereum 2. That's all for this presentation, and thanks for listening. You can reach me on Twitter at this handle, and if if you want to reach me by email, you can email me at aditya@ethereum.org.